gonna look at a nice divisibility rule. We know that 35 goes into 210. It goes in 6 times. So imagine you have 210 marbles. You have 100 marbles here and 110 marbles here. Now notice that 35 doesn't go into 100. 35 doesn't go into 110. But the total, 210, 35 goes into it. So you come along and you take away 35 marbles here, you're left with 65. You take away another 35 marbles, you're left with 30. Over here, you take away 35 marbles, you're left with 75. Then you take away another 35 marbles, you're left with 40. And you take away another 35 marbles, you're left with 5. But we know, since 35 goes into 210, that if we keep taking away 35, there'll be none left. Ah, look at this. Those add up to 35. And that's what's always going to happen. The remainder here and the remainder there, they will add up to a multiple of 35. That's if 35 doesn't go into either of these numbers. Well, even if these were both 0, even if R1 and R2 were both 0, well, 35 does go into 0 plus 0. 35 will go into the remainder. Okay. So let's write this up as a theorem. Suppose C does not go into A, and C, let me not say and. C doesn't go into A, C does not go into B, and C does go into the sum. If this, then the remainders will add up to C. Let's call it remainder from A and remainder from B. They will add up to C. And here's the proof and the clear definition of what I mean by remainder A and remainder B. C does not divide A. That means A is a multiple of C plus a remainder. But whenever you divide by C, the remainder has to be at least 0 and less than C. But in our case, we don't want the remainder to be 0. That is, C does not divide A. Now, C does not divide B means that B is a multiple of C plus a remainder. And same argument. The remainder must be between 0 and C, not including either endpoint. Now, we want to show that and we're told that C divides A plus B. Okay, so let me actually just include that. C divides A plus B means that A plus B is some multiple of C. Okay. So I'm going to add A and B. I'm going to add A and B. A is a multiple NC plus RA. B is NC plus RB. And A plus B is M plus N times C plus RA plus RB. But A plus B is KC. So KC is a multiple of C plus RA plus RB. Bringing these C's to the left, we factor out the C, and we'll have K minus M minus N C's. And this is RA plus RB. So this divides C. Sorry, C divides RA plus RB. That is, RA plus RB is a multiple of C. But let's look at something. We know that RA is between 0 and C, and we know that RB is between 0 and C. If I add, I find out that RA plus RB is not 0, and it is less than 2C. Now, RA plus RB being a multiple of C, it either equals 1C, 0C, or 1C, or 2C, etc. But it's not 0C. This 0 is the same as 0C. It's not 0C. It's less than 2C, which means it's less than 3C and 4C and 5C. That means it's 1C. This is equal to C. Okay, let's write that up more nicely. So, RA plus RB is equal to C. But that's exactly what I wanted to show. And that's pretty neat. So, for example, we know that 7 goes into 35. It goes in 5 times. Now, if you have, I don't know, 29 plus 6, and you divide by 7, just for the record, that is 35 over 7. Now, 7 does not go into 29, and 7 does not go into 6. Now, let me make that 6 a little bit bigger. Let's say 27 and 8. Now, if you do this, 27 over 7 plus 8 over 7, well, in here, the remainder is 6. And 7 into 8, the remainder is 1. And when you add the remainders, you get what you're dividing by. And that's pretty neat. And it has to be. It has to be. Because if you keep taking away enough 7s from 35, you're going to have 0. And this really is 35 divided by 7. So I took away what? 3 7s. 3 7s. And I had 6 left over. And over here, I took away 1 7, and I had 1 left over. That is, I'm going to have 4 7s plus 7s, which is 5 7s. That's exactly how many 7s I said I would get. This is 27, and this is 8. And this sum is 5 times 7. That is, 7 goes into 35. 7 does go into 35. Goes in 5 times. This is a real nice theorem and hopefully a nice proof. See you in the next video.